1st of April. We are back face-to-face with these hybrid modes, so the seminar is broadcasted. At the end, will be accepted both kind of questions from people that are physically here or from Zoom. So we will try to manage both things. So today the speaker is Diego Torres, the director of the Institute, and he's going to present some talk about the nature of gamma ray binaries. So Diego, the floor is yours.
Thank you very much. And indeed, it is for me very, very nice to restart and to be speaking in the restarting of the pizza seminar, of the in situ pizza seminar. So let me just start by discussing. Oh no, this is not working. Oh, just a click. Okay, let me start. I was scared that this was not going to work. So what's in a name? The name is, of course, the gamma ray binary name. So basically, gamma ray binaries are a class of binary systems defined by phenomenology, not because we know what they are in most of them, but because we know what they do. And because of that, there is not a very clear definition of the concept behind the name. In any case, the main two features of gamma ray binaries is that they emit in gamma rays, and especially the peak of the spectral energy distribution happens beyond 10 MeV. So gamma rays dominate the spectral output. And also they present orbital variability across all frequencies. These are the two main things that they do. And this is why, this is how we define actually gamma ray binaries. These were hinted since the early 70s, and they were studied since a satellite called COS-B, which is predecessor. It was an ESA satellite from the European Space Agency, and it was a predecessor of COMTEL gamma ray satellite from NASA. So we are speaking almost 50 years ago. Here you see the first detection of what will be the main focus of this talk, which is a system called LSI-61303 by COS-B, and this happened in 1976 in a PhD. This plot is from 1976. It's from a PhD thesis, where it was already seen with this early gamma ray data that there was significant variability in the source, or believed to be significant variability at the time. But still, in the 2000s, in the beginning of the 2000s, before Fermi, we didn't have any confirmation that gamma ray binaries were actually emitting in gamma rays. So we have hints that they were emitting in gamma rays, but since the positional error was so large, in order to associate the binary, which is, of course, a star in the sky, with a size which is many full moons in the skies, is impossible. The only way to do that was to improve on the positioning and to actually detect the orbital periodicity of the system. And this was not possible with these satellites until Fermi-LAT, which is the large area telescopes on board the Fermi gamma ray satellite, started to take data. So now, in addition to Fermi-LAT, we have other ground-based telescopes, TeV telescopes like MAGIC, Veritas, and HESS, and all of them have detected several of these systems. For instance, LSI, LS5039 is another, and then these names that I put here, 1259, 0632, and 1018. This is the only case for which we know, or we knew, what is the compact object in the system. This is a pulsar in a system for which the stellar companion is a large BE star, which is the same stellar companion that you would find here for LSI. And you can see that MAGIC and others reported a possible flare from Cygnus X1. And because it is a flare without orbital periodicity and without being dominating the spectrum in gamma rays, the X-ray spectrum is has a much larger flux. This is a different phenomenology. And also, Fermi detected signals X3 in a similar situation, and there are other binaries that have been proposed, but the evidence for them is not found yet. And also there is this microquasar, which is also a fully different case from the gamma ray binaries, also because of these two properties that appear so simple are not in general fulfilled by any other class. The last GeV binary was found recently in 2017 in this 0632 plus 057. This is a result of the gating of the pulsars in the vicinity. The problem in Fermi now is that there are so many pulsars that whenever you want to find in a particular direction what is the gamma ray emission from a particular system, you have to somehow turn off by hand the pulsar. So you have to actually characterize very well the pulsars in the vicinity and look the source of your interest where the pulsar is not emitting. So you actually reduce the integration time. You pay this price of reducing the integration time, because if you would observe along the peak of the pulsar emission, then your source, your region of interest will be contaminated by photons that are not coming from the source from your source of interest, but from the nearby pulsars. So you have actually to do quite a complicated process in order to detect this kind of sources. So at the end, there are these 5 confirmed. There are other candidates, but let's focus on this. And in particular, I will focus on this source, LSI-61303, that to me is the most interesting. And I will try to show you some results for that. Here we are speaking of a system which has a period of 26.5 days. The eccentricity seems to be high, more than 0.5, depending on the orbital ephemeris, but there is some discussion here, not in the period, but in the eccentricity, there is some discussion. Then, as I was saying, there is a BE star in the system, which is relatively massive, and you can have here some measurements for the periastron and apastron. You can see that if you were to compare these numbers, which are in astronomical units, with these numbers here, you see that the apastron of this system is actually smaller than the periastron of this other system. So the period here, the orbital period is several years, and here is just less than 1 month. So the system is much larger here. And this is something to keep into account, to keep in mind, to take into account. Systems can be very different sizes. So as I was saying, these are the main characteristics of the system I am interested in. And this is also to show some of the phenomenology that was found for this X-ray binary. This is perhaps the most impressive, one of the first results. This comes from, I think, 2005, 2006, I don't remember, one of these years. And this is the TeV observation and the TeV light curve. And you can see impressive spectral variability in the TeV regime along the orbital period. Here the orbital period is 5 days, and it is divided in about half of the orbit. So the two spectra here are about half of the orbit each. And you can see very clearly that orbit after orbit, this is there is something going on really in the system, changing a lot the physical scenario. The same was detected in for LSI-61303 in 2006. This comes from a paper of that year, in which we detected the source essentially doing the same. Around a apastron, we detected it brightly, and when the source was closing in periastron and much more affected by the star, let's say, the source disappeared. So there was a very large variability, no? Similar to what is detected in the other case. So the first generic question I studied related to this source was, what kind of particles were generated the radiation, where they were protons or electrons. So the very basic thing you can ask. And the idea is that if you have gamma ray emission that is produced by protons, the process for that to happen is proton-proton interactions. So proton-proton interaction produces neutral pions, and the neutral pions decay into two gamma rays. But at the same time, another 2/3 of the times of the, I mean, it is divided in 1/3, 1/3, 1/3. In addition of the neutral pion, you produce charged pions. And the charged pion also decay very quickly and emit neutrinos. Neutrinos, when traveling from the source to the Earth, oscillate. But all of this can be computed. So given a source, a spectra, a flux from a source that you know, if you assume that this spectrum is proton generated, you can actually estimate how many neutrinos you would detect. And this is model independent. So assuming that the whole spectrum that you have is proton produced in gamma rays, then you can actually predict how many neutrinos you would have to detect here in a given experiment with a given instrument response function. So we did this in much detail with Francis Hansen in 2006 for ICE-CSIC, and predicted that if the source was hadronically produced, the gamma rays from the source were to be hadronically produced, the system would have been detected in ICE-CSIC in the following years, just a few years. This did not happen. There are only upper limits. So I think, many people think the same. I think essentially all believe the same, that the source is leptonically generated. Then in 2009, we did detect the source in Fermi, because we could pinpoint the source location much better than in COSB or in Y, which were the predecessor instruments. And essentially because we could find the orbital periodicity of the source. These 26.5 days, we detected directly in gamma ray data for the first time, just by making a power spectrum analysis of the gamma ray data received, of the times of the gamma ray data received. And then the same happened for other systems very quickly. We started to detect the same orbital periodicity up to this latest one in 2017. However, there was already a dichotomy regarding what is the basic composition of the system, of this system and all other systems in gamma ray binary, except for the one for which we know there is a pulsar in there. One possibility is that they are the same as this case. There is a pulsar, a B star, the pulsar travels sometimes crossing and a decretion disk of the B star, and maybe that affects the gamma ray emission, and this is the origin of the variability. And in the other case is the case of a microquasar, in which you have a companion star that produces an accretion disk onto a black hole, or maybe even a neutron star, and then you have jets, and the jets also oscillate, precess maybe, and produce orbital variability, in addition of the orbital variability that you have because the star is actually orbiting, I mean the neutron star or the black hole is orbiting the companion. We didn't know for most of the sources which of these two was the real case. And why it is so difficult? Well, because if no pulsations are detected, you are never sure whether it is a pulsar or not, what you are observing. And this was a simulation that Nanda put forward in a paper in 2010. We did this. And the idea was that what would happen if you take an accretion spectrum from a given source that we know for sure it is accreting, and put it at the same flux level and at the same distance from other gamma ray binaries. Can we see the accretion lines or not? And the answer is, well, not really. So you were never sure that maybe the system was there, it is accreting, and because it is too dim or because it is too far, or both, you will not realize it. So at the end, I mean, without pulsations, this was going to be a never-ending discussion. And this is essentially what has happened. We have been discussing on this a lot. The models, however, share some essential ingredients. No? Well, the binary system has a massive star, so certainly this is given target material, photons, and there is an anisotropic inverse quantum models there. The orbit constrains the geometry in non-trivial ways, and other radiative processes like synchrotron absorption and percreation and cascading are active. The models differ in the dominance, no? So you can have pulsar wind zone processes. So the radiation, the inverse quantization, let's say, of the gamma ray photons happens within the pulsar wind, or maybe in a shock in between the neutron star and the VE star. But at the end, all of these kind of models are, let's say, relatively similar. So there is a complex phenomenology, and there is variability all around at all time scales. For instance, we have short timescale phenomenology that I will show, and we will have also burst that I will show in a minute. So the most interesting system of these gamma ray binaries has always been this LSI 61303, because it is very complex to understand. This is, for instance, coming from a paper that I put forward in 2010 and then in 2011, related to a discussion of a long-term observation with RXT, where you can see that, well, here you see the orbital period in X-rays. This was the first time that we see it so clearly. Before we have only hints, and the first harmonic of the orbital period. And then you can see how there was variability along the orbit, also in X-ray, similar to what we showed before in gamma rays. In addition, if you were to do a light curve, you can see that there are situations in which there are excursions in flux, which are significant, very significant. We detected many of these, and not only us, but other people. And if you can see here, these are the counts in X-rays, and this is the orbital phase. So different 6 months period. So cutting the data is more than 4 years. So we cut the data in periods of 6 months. We can see that there was a lot of variability in the light curves already. So something was going on also in longer time scales. You can see, for instance, here that the modulated flux fraction was increasing. At the end, we end up discovering the superorbital periodicity in X-rays. So superorbital periodicity is a periodicity in the system that is happens in a scale much longer than the orbital period, which is 1 month. So the orbital periodicity for this system happens in 67 days, which is almost 4.5 years. And this happens, it is believed that it happens in relation to a quasi-cyclical variability of the VE stellar wind, which have periods in which the emission of matter, or the density of the matter in the wind, increases. And this apparently can happen in VE stars quasi-cyclically. Other people also discovered the same thing, actually in the same journal, in the same volume of the journal, back-to-back papers. So we discovered this superorbital variability, also Chernyakova et al. With a very similar methodology did the same. We also discovered that the same variability could be seen in hard X-rays, not only in soft X-rays, but also in hard X-rays using integral. And at the end, in 2008, there were several reports of short soft gamma ray repeater-like bursts coming from the source, 2008 and 2012. So we studied this at the time very carefully, and you can see here that the durations are really very small. This is the whole duration of the burst, but typically the peak is less than 1 second, and the flux, the fluence was quite high, for the source. And what we did back in 2012 was to study possible counterparts of these flares. And we did not find anything obvious other than the system LSI 61303. This was also done in radio with the same conclusion. So at the end, we have short magnetar flares. The burst duration was 0.16 seconds. The spectrum was consistent with magnetar bursts, in particular, those observed from AXP. And you see that the luminosity was quite high for this, just in this range, in this small keV range. So, however, this is again something very indicative that what you are seeing should be a pulsar, but there was no detection of pulsations. In fact, the upper limit of the pulsations was put a few years before, and this was around 10–15% at most, which is compatible with other pulsars, which at the end were detected because of longer integration time or because they are near. So we studied, we did a search of pulsations, but we only imposed upper limits. Let me just skip. And then regarding the flares, the longer flares in the kilosecond time scale, both the microquasar scenario and the pulsar scenario could offer some explanation. So this was also not indicative of the true nature of the system. So we did find this gamma ray emission superorbital variability as well. So the superorbital variability was not only found in radio, X-ray, high X-rays, but also in gamma rays. And let me just show you briefly this. This is the GeV long-term evolution. This comes from a Fermilab paper that we published in 2013. And you can see here, again, 6 months. So each panel here is 6 months. And in green, you see the regions of periastron, and in red, the regions of apastron. So you can see that the trends for the location of the maximum and minimum are visible. No? The maximum is happening near periastron, but there is significant variability. And this is better seen when you put all of these flyers one on top of the other. You can see that there is a lot of variability, very similar to what we have found before in X-rays. And now if you take this same data, but order that in equal orbital phases, so you put together the orbital phase from 0 to 0.1, from 0.1 to 0.2. So all of this region is in periastron, and all of this region of the orbit is in apastron. And then you have a fit, which is a sinusoidal line with a fixed period at the period of the superorbital variability that was found in the other frequencies. And you can see that whereas here it is quite dubious that this period is present, as soon as you start going off of the periastron region, it is quite obvious that the sinusoidal fit is quite good. So this was used to claim that in this part, the conditions for the GeV generation do not significantly change along the superorbital period, which is 4.5 years. Essentially, you have more or less the same emission. But in apastron, there is quite a lot of change in the region, no? in the superorbital period. Further integration of data, for instance, up to another superorbital period in 2017, only confirmed these trends. So we started to develop a theoretical perspective, which we call the flip-flop model. So what could be happening? Well, let me just put this movie. What may be happening is that you have the neutron star going around the BE star, no? And at some points it is outside the decretion disk, and some other points in the orbit it is inside. And you see that the idea is that when it is outside the decretion disk, the pulsar may act freely, let's say, as a pulsar, because it is less affected by the matter in the accretion disk. Now, the superorbital variability is essentially something similar to say that the size of the disk changes in time with the period of the superorbital period. So there are phases of the superorbital period in which even in a pastron, you are inside the disk. And when this happens, the flux is lower. In phases when the superorbital period, you are outside of the disk, then the pulsar can again be active. And this is the basic idea, which then we written in formulas, but this is the idea behind what I am going to say. So this is again the idea. The idea is to say that, okay, we have a poloidal wind and we have a decretion wind. We established this model in which the equatorial disk has a much larger density than the poloidal wind, maybe by 3 or 4 orders of magnitude. This difference is not minor. And then we just compare, taking into account that for a pulsar in a binary, when matter pressure varies, different states are possible, right? So you can have a pulsar in an ejector state, which is if the pulsar is energetic enough, then it is unaffected by the matter in the vicinity. It's essentially behaving as if it would be isolated. Or you can have a propeller, or ultimately you can have an accretor. So you can have the pulsar accreting matter. The propeller phase or state happens when the magnetic radius is less than the light cylinder. But still, you are in a propeller state there. You abandon the ejector state, but you are not accreting until it happens that this is still less than the co-rotation radius. So there is a possibility that you are changing states along the superorbit. This is what we propose. So, and we actually find that this is possible for a pulsar, let's say, of relatively large. This is just an example with 10 to the 13, but it works with 10 to the 14 or with 7 times 10 to the 12 is something like this. It can work. Here you have periods as a function of the mass loss rate. And you can see that if the mass loss rate changes, and this is, let's say, the mass loss rate that you would have in the equatorial disk, and this is what you would have in the poloidal wind. So there is a significant change, right? So in principle, when you are here in this region, you can actually say that the system, depending on the period, could be changing states along the superorbit. So another way of looking at this is plotting the magnetic field as a function of the period, the surface magnetic field, the surface of the neutron star, and to say that if the apastron luminosity is all pulsar generated, the system must be to the left of the curves, right? Because we are looking a lot of luminosity coming from a apastron, more than 5 times 10 to the 35 Hertz per second. And if all of that is generated by the pulsar, then the luminosity of the pulsar should be to the left of this. These are lines of equal luminosity, so it should be to the left of that. If it could be to the left of these curves, could be an ejector all the time, if it is energetic enough, or if it is, let's say, in the white part, it could flip-flop. So it could change states. In here, in the yellow part, the maximum, if in periastron, where you have the maximum of the accretion rate, the system is still an ejector. And in here, in a apastron, where you have the minimum of the accretion rate, because of the period is so large and the magnetic field is so low, then the system is still a propeller. In between, it shifts from one to the other. So we put forward a model in which we computed which would be the probability to find a pulsar like this, if it is in there, to actually be in a propeller state. And we figured out which is the lifetime in the flip-flop state as compared with the ejector lifetime. And we find out that in principle, it is much more likely to find a system such as this in a flip-flop state than in an ejector state. And actually propose putting everything in that I said into the model, trying to explain when the system should disappear at what frequency, which should be the preferred period for this to work. And the preferred period for this to work is mentioned here with this black dot around 0.3, let's say, seconds. So putting all together, a magnetar binary, magnetar because there was these magnetar flares, not because the magnetic field of the surface is more than the critical magnetic field, no? Subject to significant changes of accretion around the orbit, seems to accommodate all observational constraints. This is what we concluded, and actually predicted several things. First, predicted that if it is a flip-flopping system, it would be natural to expect a significantly reduced TeV radiation near a pastron for the superorbital phases in which the disk is so large that also a pastron is within the equatorial decretion disk. And this has been never observed before. We had to wait for this to be tested for almost 2 years or more. And then we should also detect a pulsating period in a range where flip-flopping is possible. This is obvious. And then also, if we can track the accretion rate onto the compact object, if we can actually measure the accretion rate, let's say via H-alpha or something measuring the decretion disk, the TeV emission has to be anti-correlated with it, because the more the mass you have, the more massive you have, the less radiation you should detect. The prediction of the superorbital variability in TeV was indeed found 4 years later in 2016, where we detected all these points. So first we have all these points in MAGIC and Veritas, and then we detected this in 2016, exactly at the minimum, let's say, of the prediction. And this is the sinusoidal fit. It's actually not a fit because the period is fixed here to the superorbital period. The second prediction we did not detect because we use actually H-alpha to measure, and there is a lot of intraday variability in H-alpha. So we are changing a lot the H-alpha by a number of reasons, and then in order to compare with TeV, we would need to compare with measurements in TeV having the same integration times. And this cannot be done because in order to get a detection in TeV, you need to integrate for a significant amount of time. So this cannot be tested for the moment, at least. And now it comes to the last part of the talk, which is the radio pulsation discovery. And let me just start that there is not a lack of reasons for the absence of the detection. Why? Well, because in radio you have free absorption. And in addition, the free absorption, because of all the matter going forward and back, may have a complex temporal behavior. This can wash out the pulses, and this is why you would not detect radio pulsations. In X-rays, the upper limit that we put is compatible with other cases in which the pulse fraction was similar. And we know that there is a pulsar in there. And we observe with a very long integration time in Chandra. So there is nothing better we can do for the moment in order to detect the source. So in X-ray, it's simply too dim to be detected. In gamma rays, there are two reasons by which pulsations could have been missed. The first is that this system lies in a complex region with a lot of other sources, a lot of pulsars, very bright ones in the vicinity. So if you want to do this gating off, you are left with less and less photons because you take this pulsar, you take off all the peaks of this pulsar. You take this other, you take off all the times in which this other pulsar is peaking. And then you are getting with less and less integration time. And also because the diffuse background is complex in the region. There are molecular clouds, etc. But the main reason is that there is a large uncertainty in the orbital parameters themselves, the orbital period, the the periastron, where the periastron is located, etc. That if you are going to integrate long in order to detect the pulsation, this plays a role. If you detect the period in just 1 hour and you have the period of the orbit in 1 month, then the uncertainty in the orbital periodicity does not play a role. But if you have an orbital uncertainty in the parameters of the orbit, and the orbit is around 26.5 days, and you need several months in order to get the pulsation, as is the case for gamma rays, then this is a problem. So at the end, the best chance to detect pulsations from this system was try to observing at a large radio sensitivity, the largest possible for the minimum amount possible in order to avoid the orbital uncertainty. In a region of the orbiter where, I mean, reasonably, you would expect that the free absorption is less, let's say near a pastron. So we went with FAST. FAST is a 500 meters radio telescope that was inaugurated in 2016 and operated in 2019 in China. And it has already 10 times better sensitivity than Arecibo. It's 500 meters, a single dish. And what is interesting here is that in between these towers, you have like the receiver. So the receiver is like moving the plate. The plate is fixed, but you move let's say the receiver on top. And it's very impressive. So we did a chase of LSI 61303 since the very beginning, since the moment in which it was called risk share time, because the system was being tested at the time and it was not sure whether you would get something back, and we didn't for several years. But it was finally obtained good data in 2019 and 2020. And at the time, there was no unusual behavior in any of the other frequencies, not in Fermi or in X-rays, or in general, was like in a normal situation. So we have a total exposure of 10.2 hours, and we have one in periastron, just to see what happens if everything that I said was wrong. No, just let's look also there, and 3 in a pastron. And if you look at this, these are 1 day from one another, and these are several months from one another. And in one of these observations, we detected the radio pulsations. So this is the pulse. There was an unambiguous pulse signal of 22.4 sigma, but just in one of the 4 observations. The period was actually 0.27, let's say, seconds. And as I was saying, the pulsations disappeared in the 3rd and 4th observation, which were several months after, but 1 day apart from each other. We conducted a single pulse search also, and we detected a lot of single pulses. I am skipping some of the details here, but these are the details of the radio pulsation recorded. So this is the zoom that I just showed, and these are this is the typical output that you get from the pulse search algorithm, where you can see here the period and the p dot determination. But the problem is that the p dot determination is very uncertain, because also the orbital, we couldn't determine the orbital parameters. So there is clearly a rapid changes of conditions, because in the 4 observations, we only detected it in once. No? So what may be going on? Maybe scintillation, maybe nulling, or variable absorption. We consider the 3 of them. Scintillation is unlikely, because the time scale in which this happens would explain the disappearance of the flux for just a few minutes. But we observe for 2 hours, 2.5 hours each time of the 4 days, and separated in time. So you do not expect this to be there. And refractive scintillation could explain disappearance for a few weeks, but not by a factor but not more, let's say, a factor of 2 or 3, not just from 22 sigma to 0. So this is probably not the explanation. To me, what is most direct explanation is that simply the pulsar turned off itself. More than 200 radio pulsars have been seen to experience this kind of nulling. So 8% of the radio pulsar population turned off itself at some point. And actually the null fraction and the null length, which is the duration of the nulling episode, could be up to 90% in many cases. So most of the time, the pulsars you would not see. Actually, there are several in which you only see very, very rarely. And of course, there should be a lot more pulsars like this, because obviously the search that we have, the pulsars that we have are biased, right? Because these ones are much more difficult to detect. Well. And then the final possibility is that absorption changes, and this is maybe because the wind is very clumpy and there is absorption. This may happen, and in order to distinguish exactly how it may happen, we need to do more observations. So out of these two, this is clearly this one now. And actually, if you recall this plot, this is the fast period in this plot. So it is compatible with the system being just in an ejector, so the system being here all the time, or the system being here and flip-flopping. We do not know, because we do not know the P dot for the moment. So we do not know the magnetic field estimation. However, this point, then we said it was the best out of the multi-frequency explanation, is exactly at the period where we detected the period. So there is some hope that maybe the flip-flop is clearly there, and this is personally what I believe is the most reasonable explanation right now. So to me, this shows that a lot of work during a lot of years using theory and different frequencies to observe. But at the end, all is about to change in the mystery, no? So when we can change a given mystery to another mystery, it's like a progress. We see that as a progress, no? And first, the mystery was what was the kind of system that we were looking at. And now the mystery is, how could it be that the pulsar is off most of the time? Does it link it with rotating radio transients or with transitional pulsars, etc. So we are doing more observations, multi-frequency observations. We have redetected the pulsar already once and reconfirmed that it is not always present. And with that, I finish. Thank you very much.
Thank you, Diego, for the very, very good talk. Also for the historical perspective of the history of this source. It's very good to hear people clapping. It's very good news, actually. So what we are going to do is to take questions. So for people here, just while you're here, raise your hand. And the same online, just open up your mic or raise your hand in Zoom. Yeah, Vanessa?
So for most of the isolated objects that are sort of intermittent, they do not have a companion. Is there any suggestion that in this specific case, the actual environment could like affect the behavior and like cause that somehow?
To cause the nulling, you mean? No,
So,
there is.
Diego, can you repeat the question for them?
Yes, sorry.
This is a bit messy, but
yes. The question was whether the fact that this pulsar lies in a binary system may affect or may prompt, let's say, the possibility that the pulsar itself is nulled. And there is no indication for that. Maybe, but I do not know. I don't know enough to answer because I really don't have the pulsation well characterized. We only detected it twice. And ideally, the plan now, what we are trying to have is try to connect when the pulsar is on with the properties of the system, what the system in general was doing at the time. And for that, it's very early to tell.
Thank you. Ignacio?
Of this superorbital period, very good. Did you consider geometric changes on the orbit of the pulsar? I mean, I guess the time scale is way too short for that, but has that been considered?
The question is whether the superorbital period can come from some geometrical change in the system, in the orbit.
It was briefly considered, I mean, briefly discussed, but the time scale is too short, as you were saying, and the life of the total pulsar, I mean, of the total system is also believed to be very, very short for this to appear to be plausible.
Have another option.
Yes, this could be one reason, but we didn't detect it, that other object in variation. It is also true that we didn't have the pulsation before, and so we could only have detected this in the orbital periodicity, but not in the pulsation of the pulsar report, because we didn't know. So it's much more difficult to detect it. But then, yeah, I don't know. I think not, but it is only briefly considered in the literature, this kind of possibility.
Okay, thank you. I hope it was possible to hear the answer. We are trying out how to sort this smoothly. Any other question? Yeah, Clara? The question is the size of the accreting disk can affect the orbital period of the source.
Not the orbital period of the source, but certainly is the other way around. The system plays a role on the decretion disk, for instance, cutting it off. So essentially it is believed that the decretion disk, and there is a lot of discussion of this point in the literature, every time the pulsar enters and exits the decretion disk, affects the decretion disk a lot. And most of the matter in the disk beyond that position is actually sent off the system. So it is actually the other way around. It's not that the decretion disk will affect the orbital periodicity, but vice versa.
Thank you. Any other question? Also from online people? No? Well, then if not, finally we can enjoy a pizza. I think it's in the patio, no?
Yes.
Yeah. So see you there,
very
and thanks for coming, and also for people to connect.
Thank you.
Bye-bye.